let's do the pre-analysis before we get into ANSYS. And the first thing we will do is we will take a look at the mathematical model that we need to input into ANSYS, and then we'll go on to consider the numerical solution strategy used by ANSYS to solve that mathematical model. The mathematical model is a boundary value problem, and we are given the non-dimensional version of that boundary value problem, which I discussed before. We have to input a dimensional boundary value problem in ANSYS, and this has to correspond to the non-dimensional boundary value problem. And here's a dimensional boundary value problem we will input into ANSYS. And what I did was I worked out the corresponding inputs in ANSYS such that this problem would look exactly like that problem. First, let's take a look at the governing equation. This looks the same, and I can set any value of k, and essentially those two equations are the same. And this is energy conservation in the absence of heat generation. This boundary is easy. I just set it to 1, just like over here. This boundary is easy. I just set insulated. So instead of d theta by dx, I'm setting dt dx. Similarly over here. Okay, so there is a correspondence between that boundary condition and that boundary condition. Now this boundary condition is a little bit more tricky. So I will set k equal to 1. So here I'll set k equal to 1 watts per meter per degree Celsius. Then the left-hand side here looks like that. And the right-hand side I will set h equal to the BO number that I'm given, and I'll set the temperature of the fluid to be 0 degrees Celsius. When I do that, this boundary condition looks exactly the same as that, and then this dimensional boundary value problem looks exactly like the non-dimensional boundary value problem. And ANSYS will report the temperature in degrees Celsius, but I can interpret that as the non-dimensional temperature theta. Okay, so T and theta will be the same if we do that. So that's a trick to solve that non-dimensional problem in ANSYS.